All right, welcome to this first video of this unit where we're going to learn about solutions. Last unit was about gases, now we're going to talk about solutions. And solutions really involve water, and so we're going to talk a lot about water right now, and then we're going to talk about how things dissolve in water. And so to help us understand how things dissolve in water, we need to talk about the properties of water and why water has the properties that it has. And so a water molecule consists of two atoms of hydrogen and one atom of oxygen. And they're united by a polar covalent bond. And so that bond is actually really important in just a quick refresher, a covalent bond is the sharing of electrons. So hydrogen and oxygen share electrons. And it's polar because there's an uneven sharing of electrons. And so the reason why it's polar is because hydrogen is kind of similar in electronegativity to carbon, and then oxygen's over here. There's a difference in electronegativity, which means there's a difference in the pool on shared electrons, and so oxygen will pull those electrons closer to itself, making it partially negative, and then hydrogen is partially positive. And so all of that's a review from Unit 6. So this is kind of what it looks like here. And so oxygen is partially negative. That's the thing that we want to keep in mind. It's partially negative, and then each hydrogen is partially positive. And so what you end up with is you end up with one side of the water molecule being partially positive and the other side being partially negative. And so that's really important for everything we're about to talk about this entire unit. So now the polar nature of the water molecule allows for hydrogen bonding. All right, so hydrogen bonding is not an actual bond, it's an intramolecular force of attraction between molecules in atoms and ions. And so it's the reason why water actually has the properties that it has. And so if you take a look here, this is an example of hydrogen bonding. So we have our water molecules, and notice how the partially positive hydrogen is strongly attracted to the partially negative oxygen of a different water molecule. And then notice how all the water molecules have this attraction between a bunch of different water molecules, and that makes the molecules want to stick together. This is actually why water has a high boiling point, because it takes a lot of energy to sort of separate those molecules. It's also the reason why it has a high surface tension, and the reason why if you were to, throw some water on the, splash some water on the table, it'll beat up, because the water wants to stick together. And then there's other properties as well, but one of the properties is surface tension. And so surface tension is the inward force or pull that tends to minimize the surface area. Water has a very high surface tension, and something to think about when it comes to surface tension, what that really means is that it's hard to break the surface of the water. Now, I don't know if you guys have ever been like jet skiing or water skiing or whatever, wakeboarding, but if you're being pulled by a boat in the water and you fall and you hit the water, or if you've jumped off a high cliff and fall and you hit the water, it hurts when you hit the water. And the reason why it hurts is because that water does not want to separate. And so and because it doesn't want to separate, it takes a lot of force to separate it quickly even. And so that's why it hurts. And so the reason why it has high surface tension is because of how attracted the water molecules are. So if you take a look, that's why water beads up the way it does. It's why there's certain insects and even some animals that can scoot across the water. And if you were to put a bunch of drops on a penny, you'll see that it makes this sort of dome. And the reason why it makes a dome is because the water molecules are wanting to stick together. Now, it also has a relatively high boiling point, and this is again because the water molecules want to stick together, and as you boil a substance, the molecules and particles are separating, and they don't want to separate, so it takes a lot of heat energy to do that. And so this is kind of what it looks like there. So you can see on the image on the right, you see the water molecules in the liquid stage, and the water molecules are going to want to stick together, but sometimes they do, break apart and vaporize or whatever, evaporate. This graph, really what this graph is showing, notice the water molecule, the boiling point is very high. Notice the HF and the NH3. Now, those all contain hydrogen bonds. So the NH3, the HF, and the H2O, those all contain hydrogen bonds, which is why they have a relatively high boiling point. Now, notice as we start looking at the boiling points of other substances within the same group. So, for example, H2S, so that's hydrogen with sulfur. Sulfur is in the same group as oxygen, and then the next one, selenium, is in the same group as oxygen, and then and so on. Notice how as we go down, there is a general increase, except for this first drop is a decrease. And really, the point of this graph is to show how strong those hydrogen bonds are. Hydrogen bonds only occur in the H2O, the HF, and the NH3. Pretty much hydrogen bonded with any of these guys here, and that's what causes them to have a high boiling point. Now, hydrogen bonding holds water molecules in a hexagonal arrangement when they freeze. And the reason why, and this actually is the reason why water expands when it freezes, because as those water molecules come into a certain arrangement, they actually expand because of the hexagonal shape. And this is kind of what it looks like here. So if you take a look, notice how the water molecules arrange themselves in a way where you've got this big void in the middle there, and for them to make this shape, they have to expand. And so that's why water expands when it freezes. It's actually one of the only substances that does that. Most substances actually condense when they freeze, or when they become a solid. All right. This is a new part of the notes now. So this is on, if you skip a page, this is the next page here. So now we're going to talk about aqueous solutions. And what an aqueous solution is water that contains something dissolved in it. So if you have salt, it's solid. You put it inside water, it dissolves in the water, and it becomes aqueous. It just means that it is dissolved in water. And the solution process depends on the force of attraction between the solute, which the solute is the thing being dissolved, and the solvent, which is the thing doing the dissolving. So if we think about salt and water, salt being dissolved in water, salt is the solute, water is the solvent. In fact, water is called the universal solvent because it can dissolve many things, and it's very good at dissolving a lot of those things. Now, what I'm going to say is, before we look at the notes here, I want you to look at the animation at the top here. Notice how it says dissociation, because that's the process of ionic compounds dissolving in solution. And notice how we have the positive cation and the negative anion. Well, look what happens. Look at this animation. Look what happens here. I'm going to show it again. Notice how when dissociation occurs, the water molecules come in, they break apart those ions. And again, ionic compound is where you have a positive cation and a negative anion that come together because electrons were transferred, opposites attract. So again, let's go ahead and look at this. So notice the positive cation. Look at the water molecule. The negative, the partially negative oxygen atom is what's attracted to that positive cation. Now look at the negative anion, the ation part. Notice how the partially positive hydrogens are attracted to that that negative ion. So when an ionic compound, which is made of ions, dissolve in water, the ions separate from each other. So when we think about sodium chloride, sodium is a positive cation, chloride is a negative anion. They actually separate from each other, and they are floating around in solution. And this is called dissociation. It's kind of like the word association. Like when you associate with someone, that means you are interacting with them, but to dissociate is the opposite. You are no longer interacting with them. So this is called dissociation and is the result of the strong attraction between the ions and the water molecule. Now, something that I want to say is at the animation at the top, it shows one water molecule coming and breaking it apart. But the reality is you have all of these water molecules that are coming, and they actually, all of them pull, and we'll look at an example here. So this is a really great picture. You really need to understand this picture. The first thing I want to point out is, let's pretend it says this is a solution of potassium fluoride. And so if you look here, notice how this is a positive cation, and notice how it is surrounded by these water molecules, and look at the orientation of the water molecules. The partially negative end of the water molecule is what's attracted to this positive cation, and notice how it's the partial negative. And the reason why that is because opposites attract, and so negatives will be attracted to positives. Now look at this one here. This is a negative anion, and notice that it's the positive end of the water molecule that's attracted to that negative, again because opposites attract. And so the orientation of this is important. Now the other thing I really want to highlight is notice how it's not one water molecule, it's multiple water molecules. And in fact, it's even more than this because this is a two-dimensional representation, but this is think about it happening three-dimensionally. You have all these water molecules doing that. And so what ends up happening is when the potassium and the chloride are together, when they go into the water, you have many water molecules that are breaking this apart, and that's actually what causes the dissociation to occur. All right, and so this is a really great example again here, where you can really see the water molecules. It's the positive end of the water molecules are attracted to the negative anion, and the negative ends of the water molecule are attracted to the positive cations. All right. So the result is a solution with free moving charged particles which are able to conduct electricity. And so an interesting fact is that if you have pure water, like just pure water, not the water that comes out of your tap, but pure water will not conduct electricity. For water to conduct electricity, it needs to have dissolved ions in the solution. And so we're going to look at a really great example of that. But pure water does not conduct electricity. It's a very common misconception there. Now, the number of ions produced in a solution depends on the ratio in the original formula. And so, for example, sodium chloride is one chloride. So that's two ions that are dissolving in solution. But if you think of magnesium chloride, that's MgCl2. You have two chlorides, one magnesium. Now you have three ions going into solution. So sodium chloride has one sodium, one chloride, two total ions. Magnesium chloride is one magnesium, two chlorides, three total ions. And we'll look at examples of this. So this is the example here. Notice how we have sodium chloride. When it dissolves in solution, one sodium atom, one chloride ion, sodium ion. Go into solution, but look at the calcium chloride. We have one calcium ion and two chloride ions. And so the bottom one gives off three total ions, while the top one gives off only two. And all right, now most covalent compounds, except for acids, we're going to talk about acids next unit, will dissolve in water as intact molecules. And so what that means is they do not dissociate. So ionic compounds will dissociate, covalent compounds will not. And an example of this is sugar. Sugar, when you dissolve sugar in water, the sugar molecule stays intact. It does not break apart. And so a solution that dissolves in water to give a solution of ions will conduct electricity and is called an electrolyte. And when you hear the word electrolyte, you think Gatorade. It's called that because Gatorade has ionic compounds dissolved in it that help, replenish the electrolytes in our body, which our body needs. Now, typically, ionic compounds will conduct electric current when dissolved in water. This whole part about acids, we're just talking about this now. We actually will not talk about it again until next unit, but I will refer back to this next unit. But strong acids are considered to be good electrolytes, and we'll talk about why that is. And so a solution that dissolves molecules in water or covalent compounds, those are called non-electrolytes, and non-electrolytes do not conduct electricity. So covalent compounds, when dissolved in water, will not conduct electricity. So if you dissolve sugar in water, it will not conduct electricity, and there's pictures in your book that kind of show this. If you dissolve an ionic compound, it will. And just a quick reminder, ionic is metal and a non-metal. So if you have a metal and a non-metal that's ionic, it will conduct electricity. If you have two non-metals, that's covalent, it will not conduct electricity in solution. So typically, molecular compounds will not conduct an electric current when dissolved in water because they stay intact. So a solution that dissolves mostly as molecules but partially as ions, and we'll talk about this next unit again, those are called weak electrolytes. So we're not going to talk about this too much this unit, you won't need to worry about it, but there are some molecules that will partially dissociate, or some of them will and some of them won't. Again, we talk about that next unit. Those are weak electrolytes. They will conduct they'll conduct a little bit of electricity. Weak acids are an example of a weak electrolyte. Again, the acids we'll talk about next unit. And that's it. So key concepts: water, the properties of water, very important. The way in which ionic compounds dissociate in solution is very important. And then also what will and will not conduct electricity. And so we'll go through some example problems in class where we calculate, how many ions are being dissolved in solution and all that. So that's it for this first video. Please come with questions. Have a great day.